Okay. Hello, everyone. So I know next week's spring break, so some of you guys maybe already planned some out. But yeah, thanks for coming. So we just hang on for 1 or 2 days. Then you guys can be, have some freedom to yourself next week. Okay. Just a quick reminder. So if you haven't select the presentation date, so I will send an announcement. So right, you have to select which date, lecture you're going to do the presentation. So please do so as soon as possible, because we don't have many lectures left. I think we only have like 4 lectures left after the spring break. Then we'll go to the presentation. So make sure you complete that. And if you have any questions, let me know. As also mentioned in the announcement, if you are enrolled in the in-person session, please come to the class to do the in-person presentation. Because I don't do any attendance sheets, so this is all your responsibility. But maybe the presentation is the only one time I ask you guys, right, to come to the class to do the presentation. If you're enrolled in the live synchronized the Zoom session, you can do that via Zoom. The only the asynchronized student. I highly recommend if you can find the time to do the live session via Zoom, that would be great. Or you can come into the in-person session to meet the other, student, connect, communicate, that would be good. But understand if you have other schedules, you cannot make it either in-person or live Zoom. You can record a video, with your presentation and share with me, and I will post on the course material, okay? And also, based on the recording, I have to do the grading, okay? Okay, so for today, we'll talk about generative adversarial networks, GANs, okay? So I know, the diffusion model, right, everything, this is kind of take over the GANs, but before the diffusion model, GANs was quite popular in terms of these generative network, right? You can generate images, even generate videos. A lot of applications has been, these GANs have been applied to. Even now, people still comparing with GAN network in terms of like generation quality. So I think it would be good for you to know a little bit about GANs, right? So maybe also using that in our medical image setting. So this course will give you a very brief introduction, right? How GAN works, right? And some of the GAN variants, and how these networks GANs are applied in many different applications. So this is the GAN paper, right? So published in Europe, 2014. So it's fairly like 10 years ago. I think I did this, 2 days ago. I just want to check, right, how many citations got, and how popular the paper is, right? So it's got like 78,000, 79,000, right, citations already, right? So if like 10 years, you have like 8,000 citations per year, right? So basically you can see how popular this is, right? So the lead author is Ian Goodfellow, and you may also know his advisor, Yoshua Bengio, right? So which is one of the awardees from the Turing Award, right? So really popular and famous papers. Even now, people have been, even the diffusion models perform better in terms of quality, but GAN still used a lot for generation or other tasks. So based on the name, right, so we have, this kind of, generative, right, adversarial network, right? So the generative means we want to generate something, right, that maybe fit into a specific distribution, right? This can be, the data, generated data can be an image or text or maybe video or maybe multimodal, right? Adversarial means, right, so you may have like 2 parties trying to compete each other. We'll talk about, right, what are the 2 players in the GAN network, and of course we are training the networks, right? So this can be a CNN, or can be fully connecting layer, or maybe we can using the transformer architecture, right? So there's no specific restrictions, what kind of network you can use for the GAN framework. So you can freely choose what kind of network you want to train. Okay, just for the layman's term, right? So the the generator and the discriminator is going to be the two players in the GAN network, right? So they basically trying to compete with each other, and the generator, right, basically trying to generate, right, or to have some fake, stuff, right, images or text. The discriminator will trying to distinguish between the real and the fake, right? Try not to be fooled by the generator. Okay. So it has a lot of applications since the publish or invention of the GANs, right? So mostly in the image or video generation domain, right? So we can basically generate images, right? So actually on the right side, so if you look at all these images, right? So the face images, so they look realistic, right? So if you don't zoom in, check all these small details, like the hair, or those teeth, or whatever. But if you just take a very quick glance, right? So you wouldn't, think these are fake images, right? So they looks really nice and realistic, right? So, but all these images, these persons, people do not exist. So these are the fake images. And not just for the human face, right? But we can also generate some general objects, right? The animals, or maybe some specific objects like the balls, plate, salt shaker, all these things. And if we can generate, then we can definitely also do editing, right? So here we can basically manipulate or maybe editing the images, right? Adding smile, remove smiling, right? So adding glasses, right? So all these things we can do a lot of editing, just like a photo. You do this in the Photoshop, right? And we can also do image to image translation, right? So the previously is this is randomly generated, right? So there's no specific condition to guide the generation. It's basically generate some images that look real. But for some applications, we may some specific requirement, or we have some desired output, right? So this is the image-to-image translation, right? So basically, giving a semantic segmentation map, right? So here we have these different classes, semantic classes. Can you generate an image, right, that fit this kind of semantic classes, right, or semantic map? So this is really useful in a lot of applications, right? So you want to train some vision models for autonomous driving, right? You can collect a lot of these videos, right, using the dash cameras, but you need to do extensive labeling, right? So you have to generate this kind of pixel-wise labeling information. But if you are able to using some of the existing label map, but you can generate the corresponding realistic images, right? Of course, a lot of the content can be, changed, right? You are necessarily generate one image, right? For one particular semantic map, you can generate multiple real images that fit this semantic map, right? So maybe the color of the car, right? Some of the illuminations in the scene can be very different, but the semantic class can be the same, right? So in this case, you can generate a lot of data and maybe train a segmentation model, or maybe train an object detection model, right? So similarly here, these applications, right, you can do, the grayscale image to generate the corresponding color counterpart, right? So you can also have the input is going to be a satellite image, right? So you can generate the corresponding the map, or vice versa, right? So I give you this kind of map input, right? Can you generate the corresponding satellite image that has these kind of structures, right? The roads and the buildings, etc. And also you can do this is an input which is maybe in the winter season, right? You can see all these snow, but you can generate an image maybe have a different season, right? For example, like how UCF looks like, right, in the winter or different time or different seasons. So this is another very cool application is that maybe you are a designer or artist, right? So you can quickly draw some sketch, right? So, if you design a handbag, right? So for some of the companies, then you can, quickly draw these sketches, right? This is some style of the lady's handbag, right? Then the model, the GAN is able to generate image, right? That fits this kind of sketch, the input, right? So the list of these applications goes on, right? So I'm sure you can come up with other, applications, right? Like do this kind of image-to-image translation task. And so not only for, image-to-image translation, we can also do text-to-image, translation, right? So given a text description, then we can generate an image or a bunch of image that can fit the specific text, description. So this is also really useful. And we can also have other, image editing tasks, right? Like photograph editing, right? So you can maybe change the hairstyle, right? The hair color, even swapping the face, right? So if you want to, for some applications, right? If there's some sensitive, personal identifiable information, you want to change that, right? So you can swap out or maybe totally change a different face that you don't reveal the identity of the real subject, right? And you can also do photo blending, right? So if you are some enthusiast of like taking the photos, right? So you may using these kind of GAN technique to help you to do some photo blending or compositing, right? So to make really good, images. So rather doing some changes or editings of image, we can also do image recovery or restoration or enhancement. So one very popular application is doing the super resolution, right? So you may have some photos that may be very old photos, right? So the camera, the sensors may not be state of the art. Let's say there are some photos you took like maybe 5 or 10 years ago. The cameras of your cell phone is not high resolution, right? So you may get this kind of low resolution images, right? And you want to enhance it, right? To make it more detailed. Then, the super resolution is basically trying to have a high resolution part of the original image, right? So you can also using GANs to do the image enhancement. So and other, applications like doing the surveillance, right? Like for the public safety. If you're trying to fight the crime or trying to search someone, right? So if you happen to, find a couple of frames contain the suspect, but the camera may be far away, so the face regions are not very clear, right? Usually the subject will be very small, so you end up with a low resolution face. In this case, you can using this kind of super resolution to get a very high quality. I'm sure if you look at some of the those TV shows like what's the TV show? I think there's a lot of them. Like I forgot the famous one. So you can see those police stations, right? So they get the images. They do some enhancement. You get a very high, crispy, crystal clear images, right? So that's the super resolution image enhancement technique has been involved. Okay. And of course, we can also do video generation, right? So here, this application is do video frame prediction, right? So this is really useful in like an autonomous driving scenario, right? So can we predict the next maybe 2 or 3 seconds of frame, right? See, so in this particular example, right? So I have, this person is kind of walking behind this particular car, right? So if I'm driving towards this direction, so I want to predict, right, based on the current, video footage, can you predict the next, 2 or 3 seconds would be, right? So will this car, hitting this person, right? So this can help somewhat autonomous driving decision making, right? So should we, hit the brake, right? So wait till the person passed, or we still have time to, safely, pass, avoid hitting the person, right, or pedestrian. So we can do this kind of frame prediction. And for the medical domain, right, so which is the focus for this class, is we can also apply these technique to various medical applications, right? So all these kind of image enhancement, like super resolution or image translation, we can apply to the medical domain, right? So, for example, we can enhance the MRI reconstruction quality, right? Because these image reconstruction quality depends on how many measurements you are taking, right? So if you took a lot of measurement, you can get a very accurate reconstruction. But if you took a lot of measurement, that take a lot of time, right? So the patient have to, stay in the imaging room for like 30 minutes or 40 minutes for the MRI to complete the scan. So if you can reduce that the number of scan you require, but using these kind of computational technique, right, to enhance the quality, that will save a lot of patients the time. And you can also do this kind of image translation, right, from CT to MRI or vice versa, right? So we have like multiple modalities together to make more accurate diagnosis. So the GANs not only can be applied for generation task, right, do this kind of modality generation, we can also apply this for discriminative task, right, doing the segmentation or even do this, classification. We'll have some specific examples, right, how we can using that to do, like using GANs for segmentation task. Okay, so that's just give you like a very quick, overview, right, how GAN has been widely applied to different applications. That's why you see the GAN paper has so many like citations, right, around like 80,000 citations in the last couple of years. But now let's move on to talk about how GAN works, right? So the specific component and how the optimization objective, how we can optimize the two component or players in the GAN network. Okay. So basically, we have a generator network, right? So we'll have an input, which is a random noise. Okay, so we're always starting from some random noise, right? Follow like Gaussian distribution, and this generator network, once it's trained, it will have generate a high quality image that maybe fitting with have the similar distribution as your training data, right? So we have some of the real training data to train the model. And the second player is the discriminator, right? So as we mentioned, the generator is trying to generate image, trying to make it really like a real image, right? But the discriminator is basically trying to tell if this is real or fake, right? Just a very simple analogy is that you can think about the generator is like an art forger, right? You're trying to make an art piece to, looks really like a real one. But the discriminator may be like a detective, right? Or FBI agent, trying to distinguish between this is real or fake artwork. And so these two networks are trained together, right? So, of course, during the training, you will have some of the real images, right? You can sample the image from the real image training set. And the generator will basically take the random noise and generate some images, and the discriminator will, take either the fake image from the generator or the real image, right, from the training set, and we're trying to figure out, right, if this is going to be the real or fake, right? So this is how the discriminator is trained, right, doing this kind of binary classification task. So now we have like a very high level idea, right? So these two networks, right? So they have their distinctive objective, right? One is trying to generate really, nice and realistic image, trying to fool the discriminator. But the other, right, which the discriminator network is trying to determine, right, if this is a real or fake. And to put that into some formal, formulation, so basically we're trying to jointly optimize this kind of min-max game, right? So because they have very different, kind of like opposite, objectives. So this is how the minimax objective function look like. Okay, so we have two set of parameters we have to optimize. Okay, so here the theta d, right? We're using the subscript d to denote the discriminator. Okay, so this theta d is the discriminator network parameters, right? So this could be a CN network. So basically, the theta d is the CN network you're trying to optimize for the discriminator. And similarly, we also have another network, right, which is a generator. So this can be also another CN network. And we also have the parameter denoted by theta g, right? G indicating the generator. And this is basically the loss function, right? The objective function, right? So one is corresponding to the discriminator, and the one part only will involve both, right? So here we have the discriminator, have the generator, and this part we have the discriminator. So let's look at one by one, right? Because we're gonna optimize these two networks in the alternative fashion, right? How we can optimize it and why we have this kind of loss functions. Why? What does that mean? Okay, so let's look at let's first look at the discriminator. Okay. So let's say if we only trying to optimize the discriminator. So in this case, we don't care about the generator. So we can ignore whatever the terms, right, related to the theta g. Okay. So if the goal is to optimize the discriminator, right? So let's look at theta d. So actually, these both terms, right, contain this theta d. Okay. So the first term is we are sampling from the real the training set, right? So this p data indicating the distribution of your training data, right? So this is the real data, right? So this x is sampled from the real data, okay? And this is basically the output, right? The output likelihood from the discriminator, right? So we have d is the discriminator. This is the discriminator, parameter. So that's the output. Okay. So basically, we're trying to maximize. The first term is the expectation of the data sample from the real training set. So expectation is basically like the weighted average, right, for all these random variables sampled from a particular distribution. Okay. So in this case, we are trying to maximize, right? So remember, the discriminator, the task or the objective for the discriminator is you want to correctly classify if this is a real image or this is a fake image, right? So in this case, the data is sampled from the real data distribution. We want to maximize, right? So this is has to close to 1, right? If the 1 is the real image. Okay, so let's look at the other term, right? The second term. So in this case, we are sampling, from the random noise, right? So we have the PZ, Z indicating the random noise, okay? And we have, these G, theta, G, Z, right? So basically, this is the output, right? Produced or generated by this generator, right? And we feed that into the discriminator, right? So because remember, the discriminator will take in the real images or the fake images, or trying to distinguish between them, right? So in this case, if the discriminator is going to be really good, you want this the probability or the likelihood, right, close to 0, right? Because this part is the fake image, right? So this is come from the generator, right, G. So you want the discriminator able to tell this is a fake image, right? So the likelihood should be close to 0. Okay, so that's indicating that's a fake image. Okay, so in this case, right, I here just for you to understand is plot these log functions, right? So why maximization? This is easy to understand, right? Because we want to maximize that probability close to 1. But here, because we have this minus sign here, so we have the 1 minus. So basically, if we maximize this term, we're basically trying to push, this D parentheses here, trying to close to 0, Okay. Is this clear? Any questions about this part? Okay. So next we can look at the generator objective, right? So we look at the discriminator before. Now let's look at generative model, right? So what is the generator's the objective? So the first term, the good thing is we don't have any parameter, right, related to this generator, right? So there's no theta g here. So we basically don't have to care about this term. So we only have to care about the second, right? So that's the one we also have the theta g here. So so just to recap, right? So the goal of this generator is trying to generate something that is trying to fool the discriminator, right? So basically, trying to minimize the objective such that, right, this term is close to 1. So what does this mean? That means, right, the DGZ predict, or if this is 1, 1 means real, right? So the discriminator think this is a real image, right? So it thinks this is a real image. Then in this case, we can say that the generator did a very good job, right? Because the general image, the discriminator is going to say this is a real, right? So you basically fool the discriminator, right? Because you are generating image, but the discriminator couldn't tell, right? It thinks this is a real image. So that's the objective, right? We want to fool this. The generator tries to fool the discriminator, right? So you want that to be close to 1, okay? So that's what this objective trying to push, right? So this DGZ is going to be close to 1, okay? So that's the generator objective. So to implement the optimization, right? Because we have this min-max optimization, and usually we'll do the SGD, right, in the alternative fashion, right? So we basically first doing this gradient ascent on the discriminator, right? So because we are maximizing, and we can put like a minus sign to the gradient ascent. And we can also, in the next step, we do the gradient descent on the generator, okay? So that's how we can, doing the alternate optimization for these two, networks. So this is basically like a pseudocode, right? So how you can do the GAN training. So we can specify a number of training iterations, right? So maybe for the case step, right? The first case step, we will, do the sample mini batch, right, of these M noise samples. And we can also sample a mini batch of the real images, right, to form the P data, right? So that's the real training data. And we can, update the discriminator, right, based on the discriminator function objective. So we can do this a couple of times. Then we can alternating, doing this optimize, switch to the optimization for the generator, right? So basically we sample N noise samples and using the generator objective and to do this. And we can do this for a couple of iterations, right? So that's the alternative training strategy for the GAN training. So because for the GAN training, we have these two networks, right? And we train this in the min-max fashion or objective fashion. And so there's a lot of, training tricks we have to follow, right? So actually there's some talks about, training the GAN is really, difficult because sometimes, you're training these two networks together, right? It has, a lot of issues that you result unstable training. So maybe some of the, take longer to converge or maybe has some diverge issues. So there's, some of the follow-up works, right, like this Western GAN, have a different type of a, distance measure trying to stabilize the training, right? So, there's many different training recipes you can follow, for the GAN training. So once the GAN is trained, right? So what we can do is using this generator, right, to generate image. Okay. Question?
I have a question. Could you go over to the previous slide?
Yeah.
So in the second one, should we update the generator by descending its stochastic gradient?
It depend. No, here we can do the. Is it? Did I make a mistake here?
In the last line of for loop.
Which one? This slide?
No, the next slide. Next slide. Before the last equation, update the generator by.
Is this slide or previous?
The next one. Yeah, this one. Update the generator by ascending its stochastic gradient improved objective. So shouldn't it be by descending its gradient? By descending its stochastic gradient.
So we have to look at the minimum, right? So if you do the maximization, you can do the gradient descent, right? So if it is minimized, we do the ascent. You can add a minus sign and still do the gradient descent, right? Because usually so I think I do the opposite, right? We minimize the loss function, we're using the gradient descent, right? If you're doing the maximize, you can do the opposite, right, which is ascent. Or you can put a minus sign in front, and you can do the gradient descent. So, did this one, did I made a mistake here? This is ascending. Yeah, is this like a conflict? Did I make a conflict here of the ascending? Did I say descent here? Okay, maybe there's, I need to check back this paper if they, but the general thing is that if you, usually we have to minimize objective function, right? So you're using the gradient descent, okay? But you can, if you're doing the opposite, right? If you're doing the maximize, we can do either you can put a minus sign in front, then you can do the gradient descent, or you can just do the gradient ascent. Yeah, let me go back and check. Maybe I made a mistake, have this conflict here. Okay.
And another question. So sorry.
Yeah.
So here, yeah, for minimizing the objective function, that is the generator network. Right. In generator network, like if we want the d theta sub d to be like 1.
Yes.
And sorry, in the previous one, so we want that to be 0.
Which one?
U1. So yeah, so we want that d theta sub d to be 1 in case of the generator network. Like the second part of the equation, we want that to be like 1 minus 1, right?
Yeah, so we want to maximize, the generator generates something that's real, right? So I now understand why this is ascent, because here we have 1 minus,
Yeah.
right? So here we basically remove that,
So,
right?
okay.
So that's why you have to do the opposite.
But
Yeah.
if it's 1 minus like 1, so doesn't that
So-
become an undefined, or like how do we remove it? If it's log of 0, how do we like remove it?
What do you mean, like log 0?
In generator network, we want the second part to be
Yeah.
1 minus 1, right?
Yes.
1 minus 1. So if it's 1 minus 1, then like.
I don't think you will actually have close to 1, right? So, but it's close to 1, but I don't think this will actually produce a 1. I mean, you can always clipping some of the values, right, to avoid like the negative infinity, right?
All right.
Right, so, but you understand the objective, right? So here, if this is 1, 1 minus 1 is 0, right? Log 0 here is kind of close to the negative infinity, right? So we're trying to minimize that, right? But yeah, I think just to your question, why this is ascent, because we remove the minus sign. We have to flip, right? Whatever the direction is. Okay. So once the network is trained, right? So we can using the generator to generate images. Okay. So we can sample this random noise, right? Then we can generate image that hopefully this generator is trained well, right? And you are able to generate some realistic images, right? Just like resembling the training data. Okay, so here I list a couple of like the tutorials or maybe some of the useful tricks, right? Like how you can train again. So like how you specify the learning rate, right? And how many steps, how many iterations, alternating those two training objectives. So if you are training again, maybe it's a good idea to look into these training recipes, right? Too, so you can follow that. So you have a very stable training. Okay. So next, let's talk about condition GAN, right? So before the original GAN or the vanilla GAN is we can, once it's trained, right, we can sample from noise and just generate some arbitrary images. But for some of the tasks, right, we want the generated image maybe fit some or follow some of the conditions, right? Just like a couple of applications I mentioned, right? So maybe the images, not just random like street view images, but following some specific conditions, right? So the condition here can be the semantic, segmentation mask, right? So the general images may fit this segmentation mask, or the image can fit this type of a sketch, right? Or maybe this kind of thing. So can we, in this case, one question we want to ask is, can we using the vanilla GAN to have this kind of condition or generate some images that fit this condition, right? So if you want to using the vanilla GAN to generate, what you do is maybe you take this as the input, right? Rather from the random noise, you take that like a sketch here, you feed it into the generator and you can generate an image and you ask the discriminator to determine if this is a real or fake. So in this case, right, if you do this again, right, in this time, the generator may generate a bag may look like this, right? But the discriminator will only tell if this is a real or fake image. So based on the knowledge of the discriminator, this is also look like a real image, right? This is real too, but for our application, it does not necessarily fit the condition, right? Look like this, because ultimately, this is our desired output, right? So we want to generate a real image, but also will have looks like or fit the condition with like a sketch may look like this, right? For this one, it's also a real image, but it's just not our desired output. Okay, so in this case, right, how do we solve this issue? So this is how the conditional GAN works, right? So basically, you are also taking some of the kind of like a label information, right? So we want to take the kind of pair, right? So here we have this condition X, right? And this is the generated image, and this should be like a real pair, right? So this generated image fits this condition, and this is the desired output we want. And so in this case, right, so we, in the formulation, we have the generate image, right? We also have like the corresponding label, right? So this is our desired, right? So fits the condition, and this is the generator, objective, right? So you can generate image, but this could be any of the images may do not fit the condition. So the discriminator will take both this condition and also the generate image into the consideration and to decide if this is a real or fake pair. So basically, it will match the joint distribution, right? So not just necessarily the data, but also the label information. So this is how the condition GAN works, and what other laws they also consider. So we have this usual GAN loss, right? So this GAN loss right here. We'll also have another basically kind of promote or facilitate the image generation, right? So you have this L1 loss. So basically measure, the generated image and also the real image, right? How close they are. So they're using the L1 loss, trying to promote or make the image like sharper, right? So if you're using the L2 loss, so this is like more prone to smooth output. But basically, you can add this kind of image quality, measurement as additional loss to guide the generation, right? Addition to the GAN loss. So once the conditional GAN is trained, then you can do this kind of conditional generation, right? So you have this input, and you can generate image that fits this kind of condition. So that's the sketch to image generation. Okay, so more example. And they also have this kind of like a live demo, so that you can randomly draw some sketches and using these condition GAN to generate an image look like this, right? So even if this one doesn't look like a cat, right? But you want to generate something that fits this kind of conditional input, right? So you can still do that. And another example is you can using the map to generate the corresponding satellite image or aerial image. And this is the ground truth. So you can see a lot of these kind of structure, right, kind of fits the condition, right? So this is how the road structure look like, right? So we have all these different roads, and the general image is also gonna, follow this kind of road structure, right? Although some of the places, like the building, the details may not look realistic, right? So like there's a lot of distortions on these small building, the roofs, but overall, right? So the structure, kind of look very similar to the ground truth. Other examples here, doing the color to, the grayscale to the color image translation or generation. Okay. So the next work I want to talk about is the unpaired image-to-image translation using cycle-consistent adversarial networks, right? AKA the cycle GAN. Okay. So this is also very popular work, right? So people using this a lot for image translation. So the problem statement is that, right? So the conditional GAN doing this kind of image translation requires this kind of paired image, right? So you require you have maybe this sketch like this, and the corresponding ground truth real image. Right, so you have this pair of image, right? So this one semantic map and also the ground truth image. But for other cases, right, you may not able to construct a training set that is paired, right? So for this kind of applications, it may be easy for you to collect this kind of paired data because you can have artists, right, to draw this or based on this. Real images to generate this, kind of sketch, or maybe just simply using some edge detection model, right, to detect these edges and using that as an edge map for input, right? So you can generate a lot of paired samples. But for example, for this application, right, I want you to generate like this real photo to some like a Monet painting style, right? So you cannot find like the one-to-one correspondence, right? Because Monet never paint a building like this, right? Or maybe a scene like this, right? So you have unpaired images basically, right? You have the photos, but you may collect some or like Monet their painting or maybe other artistic paintings, right? But not necessarily corresponding to the same scene, right? So this is not in this case. These are unpaired images, right? So in this case, how can we train this model to do this kind of image translation, right? Here's maybe more easy to understand cases, right? So if I want to, translate from the horse to zebra, right? So you cannot find like this horse and its corresponding zebra, right? It's not possible, right? So what you can do is you can collect a bunch of horse images. You can also collect a bunch of zebra images, but they are not one-to-one paired. Okay, there's no one-to-one correspondence. Okay, but so this paper trying to address this problem, right? So that's why they called this unpaired, and they are propose this idea called psychoconsistency. Okay, so let's see what is their idea, to facilitate this kind of unpaired image translation training. Okay, so let's look at, right, so for the X, which is the horse image, okay, and we will have a generator. Let's just call this like a zebra generator, okay. So from X, we'll generate a zebra image, right, so we have GX, right, so these are the, maybe change the horse to the zebra image. And now we have another generator, okay? Before we only have like one generator, right? So, either from one specific condition, right, sketch to an image, or from a random noise to generate image. But here we have two generators, okay? So G, for this particular example, let's just, remember G is like a zebra generator, okay? From horse to zebra. And F is going to be a horse generator, okay? So that is coming from the zebra domain to the horse, okay? So if you, this is kind of like unroll, right? So, but if you, kind of connect the, XGX and FGX together, it's kind of form like a cycle, right? So you are starting from the horse, right, going to the zebra, and then you're going back to the horse, right? So that's kind of like considered as a cycle. So the intuition is that if all these generator has been trained well, right? So if my original is this image, I go to this generator zebra and then coming back, this X hat should be close to the original input, right? So because I'm starting from this particular horse image, right? I'm using this as a style transfer to the zebra, and I kind of transfer back to the horse, right? So then the X and X hat should be close to each other, right? So that's called the cycle consistency, right? Because I go from this cycle, and this should be, the X and X hat should be close to each other. Okay, so this is another graphic illustration, right? So if I coming from this domain, go to the other domain, and I come back, and their distance, the feature distance should be close to each other, okay? Okay, so that's the, the basic idea, right? So how we can, even without this kind of paired image, right? So how we can using this kind of cycle consistency as the optimization objective, right? So basically, we want to minimize, the reconstruct, like this X hat, right? And again, here they are using the L1 loss. I don't know why you keep playing this. Okay. So in this case, you can have like a one cycle, right? So you have from the horse to zebra and going back, of course you can go the other direction, right? Like a bidirectional. So from the zebra going to the horse, then come back to the zebra. So again, you have another cycle, right? So again, you can minimize the reconstruction error, right, from these two domains. So they are using this kind of cycle consistently strategy to train this model. And then once this is trained, and we can using this to do this kind of unpaired generation, right? So in this case, once the model is trained, if this input is like a painting style, right, we can generate a corresponding photo, right? It may look like the painting, and we can, have more examples, right? So this is the painting, and we can generate the corresponding image may look like this. And here's another example, right? So like you want to change from orange maybe to apple, right? So you can also do like this. And this is the example, right? So from horse to zebra. Although as we human, we can see that, right? This is definitely a fake image, right? This is not like completely follow the characteristics of the zebra, but it's just the model how you can translate, right, from the horse, like the shape, the style, to the zebra. This is another example. And of course, we will have some failure cases, right? So like a lot of these background has been, changed to like a zebra style. And we can also do this for video, right? We can take each of the frame and do this cycle, again, using this generation. But easily you can, a lot of these artifacts, unnatural things, unrealistic, generation can be spotted, right? So, yeah, so this is like a real zebra image as the reference, right? So there's going to be a lot of difference, but it's understandable. We're just only based on the original frames to do the translation, but not really understand the unique characteristics of the zebra image. Okay, so those are some of the different variations based on the original GAN, right? So it's serving different purpose or different settings. And now we can apply these GAN, right, to some medical imaging applications, right? So one, popular application is we can basically generate between or cross modalities, right? So as I mentioned before, for some of the imaging modalities, for one particular patient, you may not imaging, get multiple imaging modalities at the same time, right? Usually you maybe take only the CT scan, or maybe you take only the MRI. In this case, we can, using these kind of GAN technique, trying to generate new modalities, right? So here we have the MRI image, then we can, basically synthesize or generate the corresponding CT. Right, and this on the right side, this is like the ground truth CT image. As you can see that the generator is pretty close, right? So to the ground truth. So in this case, you may have very good, diagnostic, function, even using this generated CT, right? The doctors may look at this and maybe can have more information, right? Because the CTs, they provide more, better on this kind of, like a bones, hard tissue, right? The MRI is more on the soft tissue side, right? So if you have these both imaging modalities, maybe has more, accurate diagnosis. And we can also using GANs to do the denoising, right? So basically, you want to remove some of the noise, right? So this could be caused by the low dose CT, right? So you don't have enough ionized radiation. For the safety, purpose, right? So you don't want to emit too many ionized radiation, but if in this case you won't have a very high resolution image, but you can using this kind of again technique, trying to enhance the image, right, to get a high resolution or denoised CT image. So so this is how their method using GANs, right, to kind of enhance a low dose CT, right? The low dose means you don't have a lot of ionized radiation. You will get a very low quality CT reconstruction. So in this case, they are using this low dose CT as the input, right? Using this generator to generate this kind of virtual high resolution CT, right? And of course, during the the training, you can generate, you can formulate this kind of a training pair, right? So for example, you may have the high resolution CT images, right? You can do some like downsampling or adding the noise to simulate a low quality version. And then in this case, you have a paired image, right? The low quality CT image and also the high quality original CT image, using that as your training data, right? So that's why they have this real pair and also virtual pair, right? The virtual pair means X is the low dose CT and the Y hat is the reconstruct, right? And you can using that feed into the discriminator on trying to tell if this is a real pair or fake pair, just like the conditional GAN we talk about, right? In addition to this GAN loss, they also have some sharpness measure, right? So basically, they want to take some of the measures, trying to make sure like the images generated are very sharp, just like the conditional GAN. They are using this L1 loss, right? So here you can also using the L1 loss or maybe other metrics to improve the sharpness. Okay, and another example is they are using MRI to CT synthesize, right? So in this case, they are using the cycle GAN, right? So a lot of applications we cannot, we don't have this pair, right? So the CT and MRI, right? Only if you have, you ask the patient to go through the machine that can simultaneously scan MRI or CT, right? Otherwise, you cannot generate a paired image. So the only thing you have is the unpaired, right? So you have a bunch of MRI image maybe from different patient, or you may have a bunch of CT images from another group of patient, right? So you can do this unpaired image translation using the cycle GAN, right? So this is their result, right? So input is the MRI image, right? This is the synthesized CT, and this is the real CT, and they also show the difference, right? This is the difference map, right? Which part may not be, doing reconstruct so well. So they analyze that by showing the difference map. So the generation is one, widely used application for the GAN network. But of course, we can also use GAN for some discriminative task like classification or segmentation, right? So in this case, how can we use GAN to do semantic segmentation? So what we can do is, so for a given input image, right? So this is like a X-ray image. The generator can be, maybe a segmentation network, right? As we mentioned, right? So these generator or discriminator, the network can be, arbitrary, right? So you can feed into a normal CNN network for classification, or you can using this kind of UNet, right? Encoder-decoder structure as your generator. Okay, so in this case, the generator will be generating a prediction mask or a segmentation mask. Okay, all the previous examples we mentioned is the generator trying to generate some images, right? But in this case, we can ask the generator to generate a segmentation mask, right? And then we can compare with the ground truth, right? So we can say this is the fake image, right? And this is the real image, right? Ultimately, the generator's task is trying to generate something that is indistinguishable from the real, right? If that objective can be achieved, then that means the generator can generate or predict really accurate segmentation mask, right? So that's the, the intuition, right? So hopefully, this is easy to understand. So basically, you can train the generator to generate these masks, and also have a discriminator, right, trying to tell if this is a real or generated mask. So once the network is trained, then basically you can using the generator network as your semantic segmentation mask. Network to do the segmentation. Okay, here's another example, right? So we can do brain signals to image generation, right? So this is kind of like interpreting somebody's mind, right? So you have, for this particular application, is the subject is wearing these EEG, device, right? So a lot of these electron nodes has been attached to the person, right, to collect its EEG signals, and we can basically train a generator, right, based on the EEG signal. What is this subject is looking at, right? The particular image, corresponding to this specific EEG signal. Okay. And collecting these kind of paired data is not that difficult, right? So basically, we can collect data in the controlled environment, right? Ask different patient, look at different images, then we can collect the corresponding EEG signals. Right, and so we can have a pair like EEG signal and a corresponding image. Okay, and then we can train this generator in this GAN network. So in this case, right, so they have the EEG signal. They also have the noise, right? So they kind of concatenate them together, right? So this is like a conditional GAN generation, right? So you have given this EEG, and you want to generate an image that is close to the corresponding, the real image maybe this person is looking at, right, corresponding to that EEG signal. So once the network is trained, then you can deploy the generator, right, feeding the EEG signal and trying to predict, right, what is this EEG correspond to. So in this case, they did some studies, and the generated image is not. Some of them are okay, but some of them has a lot of distortions. But you get a sense, right? So you get a rough idea, right? What exactly this person is looking at, right? So these are corresponding. You have some, specific shape like airplanes, right? This one has some like a panda, right? So although there's some images, maybe like a mixture of multiple pandas here. But at least you kind of know the person maybe look at the panda image or vice versa, right? So I think this is really good applications for like a brain-computer interface, right? So so we are able to kind of interpret what the person look like. Trying to think about or reading. So given all these successful cases, right, we are able to generate a lot of realistic image that also brings a lot of issues, right? So this is called the deep fake, right? So deep fake means you are generate images or videos that really indistinguishable, right? So like a general audience may not able to detect if this is like an authentic image or video, or maybe this is generated by AI, right? So actually, with the diffusion model, this is becoming more and more, critical issue, right? Because this can spread out a lot of misinformation to the public, right? And that can cause maybe some catastrophic disasters, right? If you can, generate, like the president giving a speech or making some decision or announcement. If this is AI generated, right, and spread out into the social media, then that can cause a lot of catastrophic, outcome, right? Maybe stock price can crash or whatever. So we want to come up with some of the techniques, right, trying to detect these generated images, right? So there's a very active research areas that is focused on detect these generated images, right? Looking at these details, or maybe examining from the frequency domain, right? So if there's some frequency artifacts, and also if this is video, we want to see if there's some motion artifacts, right? If unnatural motion, exists in these videos. So I just want to mention this. So just to help get you aware, this is a really critical issue. So with all these advanced technology, also comes great responsibilities, with these ethical issues, right? So we have to be mindful about this. So if you are interested in this kind of deepfake detection, so you can look at some of the references I listed here. But obviously you can search like deepfake. You'll have a lot of work here, and even Meta, they released a data set, a very large database for deepfake detection. Okay, so if you're interested, you can search Meta deepfake. So actually, this one I think is maybe from the Meta data set. So yeah, if you're interested, you can check out the data set. Okay. Okay, so that's all for today. Any questions before we end the lecture? Okay, cool. So yeah, thank you. I'll see you the week after. Okay, so next week we don't have any classes, but we'll continue after the spring break. Okay, all right. Thank you, everyone. All right.